Happy Monday, everyone. It's Mr. Swank with another Chem 1 lesson. Today is Monday, May 4th, and we are talking about uncertainty in measurements. So let's start every day like we usually do with a joke. Did you know that if you arrange all the letters in the post office, they get really annoyed? I would. I'm supposed to deliver those letters. So today, our objective is we're going to define accuracy, precision, and significant figures. As I said, we're doing uncertainty in measurements. That goes back to what we talked about last week, where we talked about how to measure, doing qualitative, quantitative, that kind of thing. We're still focusing on quantitative because there's a lot of stuff to go with that. And today we're talking about uncertainty. Uncertainty in measurements. Numbers aren't the only part of our measurements, okay? We have to have accuracy and precision. So what do I mean with that? Well, accuracy and precision, number one, are not the same thing. They get used as synonyms a lot, but they are different. They are important, and you should have both of them, but they are different. We're going to talk about that, okay? So we're going to talk about what is accuracy and what is precision. But for a second, let's talk about uncertainty in measurements, okay? Every measurement you take is going to have a tiny bit of uncertainty to it, and that is because, think about when you measure something. Wherever something lines up on a ruler, you're kind of estimating as close as possible to where it is. You can't get exactly down to the, say 16th of an inch or a millimeter. Like there's always that little bit. So you have to estimate. But if you estimate correctly, then you limit the amount of uncertainty in your measurements. Okay. So let's move on and talk about accuracy and precision. Accuracy is how close a measurement comes to the actual or true value. What does that mean? That means that your measurement is as close to the correct answer as possible. Now, this really comes down to two main things. Number one, how close are you estimating? And number two, the device that you're measuring with. You want to use a measuring device that goes out as many digits as possible. Example, when it comes to volume, beakers are not accurate measuring devices. They only have markings every 50 milliliters typically. So if something ends up between, say, 150 and 200, you've got to estimate somewhere between 50 and 200 or 150 and 200. It's a lot of estimation, a lot of uncertainty in that. But if you use a graduated cylinder, they have markings at every milliliter. So you can get as close to a single milliliter as possible when it comes to your measurement. A graduated cylinder is more accurate than a beaker. Okay? Accuracy can be attributed to something like when you're playing darts or you're target shooting. Accuracy is how close your shots get to where you want them to be. For example, if you want to hit the bullseye, you're accurate if you're hitting the bullseye. Precision is different. Precision is how close all measurements are to each other. That means when you're taking measurements, you want to be consistent. That's what precision is. Precision actually has nothing to do with how correct you are. Precision has to do with consistency. You want to consistently make the measurements the same way. Okay? For example, if you're taking measurements with volume again, you want to consistently use a graduated cylinder because then your measurements are going to be close to each other. Okay? Now here's the deal though with precision. You can be precise without being accurate. Example, let's look at the dartboard here. Let's say you want to hit the bullseye. You throw 3 darts. They all end up here in the 5 region. Are you accurate? No. But if they all end up in the same spot, in that 5 spot, there, are you precise? And the answer is yes. But when it comes to taking measurements, you want to have both accuracy and precision. You want to be correct and you want to be consistent. In order for us to maintain accuracy and precision in our measurements, we have to focus on, again, the tools we use. Okay? That's important. Example, I have a meter stick here. Okay? Let's say I take a measurement on that meter stick and it ends up about there. Look at that there and tell me what you think the measurement is. You know that meter stick is a meter long. Do you have an idea? You probably said, that's about half a meter, 0.5 meters. That's not a bad guess. The line goes about halfway through the meter stick, so that's Pretty good guess. Let's take a look, though, using a meter stick also, but the one that's a bit more accurate in its measurements. That line's going straight down, and you can see there that right here is 0.5 meters, but the line's just a bit past it. So is 0.5 meters an accurate measurement? It's not that close to the true value. We can estimate just a bit more. And since it's above 0.5 meters, what do you think it is? I think it's about 0.51 meters. Maybe you say 0.52. There's a little bit of guesswork in there, but nonetheless, you can take a look here and see that our two measurements aren't exactly the same. That line is in the same spot on both meter sticks. It's going straight down. So between those two measurements, 0.5 meters and 0.51 meters, which one is more accurate? Which one is closer to the true value? Hopefully you said the 0.51 meters, because we can see here that it goes a little bit past 0.5, so it's not just 0.5 meters. It's 0.51 meters. Now you can see that the top measurement and the bottom measurement there have different amounts of digits in them. This is what's called significant figures, okay? Significant figures are the digits in a measurement that are absolutely known plus an estimated final digit, okay? Think about that definition for a second. Go back here. The digits in a measurement that are absolutely known plus one final estimated digit. If we look here at 0.5 meters, that 5 is an estimation, is it? Do we know for certain, just looking at this top meter stick, that it is 0.5? No, we estimated because we saw it was about halfway. That's only one significant figure. It is that final estimated digit. But if we look down here at this meter stick, we can see that the line goes just a tiny bit past 0.5. So I know this 5 is definite. That is absolutely known. If the line is between 0.5 and 0.6, that 5 is absolutely known. The 1 here is my final estimated digit because it goes slightly past that. Okay? This has what we refer to as two significant figures. The more significant figures in a measurement, the more accurate the measurement. Okay? This is what goes back to me saying you've got to use the appropriate tool to measure. You want to use something that has more markings on it that you can get closer to the true or actual value. Significant figures keep accuracy and precision because the more sig figs you have, the more precise you can be and the more consistent you can be. This helps to eliminate error and give you a better result in the conclusion of whatever experiment it is with your data. Keep in mind, though, that significant does not equal important. Digits that are not sig figs are still important. By the way, sig figs is how we abbreviate significant figures. But every number in a measurement is important. Significant figures count towards the accuracy and precision, but all the numbers are important. I cannot stress that enough, okay? All digits are important. All right, guys, that wraps up our lesson here on uncertainty. So this is the first day. We talked about accuracy, precision, and how to keep that with significant figures. Make sure you do that assignment that's been posted. And tomorrow, we're going to talk more about significant figures and how to identify them in a measurement. But for this lesson, I'm Mr. Swank, and I'll catch you guys tomorrow.